All right, you guys, example number 4 is going to walk us through a second error propagation problem that involves differentials. So this example says, consider that you're completing a lab in which a cubic box is used to measure the pressure at different depths underwater. So as you go underwater, the pressure is going to increase. So you might be interested in seeing what kinds of pressures this box could withstand. And so it's a cubic box. And so if you guys can put up with my never fantastic box artistry, we've got this kind of cubic box setup. So if we're trying to calculate things like surface area or volume in this case, we only need to measure one side length. So the side length that we measure is that it is 9.2 plus or minus 0.05 inches. So we're still not measuring in a very precise way, but we're slightly more precise than we were in the previous example. So here it says, what is dx? So what that means is the differential in the value that we're measuring. So if you wanted to call that ds to represent differential in side length instead of dx, that would be just fine. And so that's our 0.05. That's just the error in our measurement. So then we can calculate the volume. So the volume is going to be a length times the width times a height. And since we have a square box, so all sides are square here, that's just going to be s cubed. So here we can take that 9.2 and we can cube it. And so when we do that, we'll get 9.2 raised to the third. So that's going to give you 778.688. So one thing that you want to keep in mind is that the way that you report this information is going to depend on the significant digits work that you're doing in your science class. So right now I'm going to round that to 1 decimal place because my original measurement was 1 decimal place. What you would actually want to consider for this in science work is that you've got 2 significant digits in your measurement, so your calculated value is going to have 2 significant digits as well. But again, that's not our focus here. Our focus is in how the error propagates, not in how the significant digits carry. So the error in the volume calculation, I can call dV, and I find that by taking the derivative of the volume, so s cubed becomes 3/8 s squared, and I multiply that by ds. So what that means is I can take 3 times 9.2 squared, and I multiply it by the error, which is 0.05. So when I do that, 3 times 9.2 squared times 0.05, that's going to give me, again, I'm just going to round to 1 value after the decimal place. That's going to give me 12.7. And these values should both be in inches cubed because we're working with volume here. So that's my volume. That's my propagated error. So the relative error I can find by taking the error in the volume and dividing it by the volume itself. So that's going to be 12.7 divided by 778.7. The units are going to cancel here. So when I do that, 12.7 divided by 778.7, I get 0.0163, which is going to be 1.63%. All right, you guys, I paused that for announcements, but the next calculation we want to do here is the surface area calculation. So the surface area we can find for a square box is 6x squared. So we can find the error in the surface area calculation by taking that derivative and multiplying by its differential. So to do the surface area calculation, we can just do 6 times 9.2 squared, and that's going to give me 507.8, and that's going to be in inches squared. Then to find the error in that measurement, we can do 12 times 9.2 times 0.05. That's going to give me 5.5 inches squared. So then to find the relative error, all I need to do is take the error in the surface area divided by the surface area itself. So that's going to be 5.5 over 507.8. 5.5 over 507.8 gives me 0.0108, or about 1.08 or 1.1%. So just like before, we see that the error in measurement for the surface area is less than the relative error in measurement for the volume. And the reason for that is we have a smaller exponent, and so we are propagating the error less. That's the idea here. Now this next example, example number 5, that's going to deal with an extended topic that takes us a little bit beyond the AP exam. So I'm going to go ahead and pause here, and I'll upload this example 5 in a minute. This is going to be one that won't be required for your quiz, but it's one that I would strongly recommend understanding because of how useful it will be if you go on to do college science work that is laboratory based. So go ahead and check out another video for this one, and then we will go over this content and warm up tomorrow together.